Alright, so in this chapter we talk about the limit, but in order to talk about a limit we have to talk about slope. So back in 1648 Newton wanted to find the slope of a tangent line that touches in only one spot on some curve here, this circle. You can try to find the slope of the tangent line, but tangent line is not supposed to cross a function in two places, only in one, so sometimes it gets a little confusing as to what an actual tangent line is. So what Newton did was he took a basic equation of y equals x squared, a basic parabola, and instead of finding a slope of a tangent line that touches in one spot, he said to find slope you need 2 points, which is correct, and he picked 2 points on his line, the one point he wants to eventually get to, and then a point nearby. And what he ended up creating was what's called a secant line, because it touches in 2 spots. And you can find the slope of that line pretty easily just using the slope formula. Remember, the slope formula is just y2 minus y1 over x2 minus x1. Alright, so you're just using the slope formula in this section over and over and over again. And what he does is he moves this number closer and closer to the point 1, 1. And when you get infinitely close to this point, you can tell what number your slopes are approaching. So if you look as you get closer and closer to 1, your slope here gets closer and closer to 2. Now if you get closer and closer to 1 from below, again it gets closer and closer to 2. So our slope should be 2 on this one. Alright? Now, this is his idea here of doing the slope of the tangent line. You start with a point P and a point Q that's above it, and you get this slope. And then you pick a point that's closer, and you get something that's a little more accurate, and you get something that's even closer, and you get even more accurate. And then you can do from below. This point is below Q, or below P. It's way over here in the negative X values. And then you pick one that's a little bit closer, and then you pick one that's even closer yet. And as you get closer and closer from either direction, you will eventually get to the number that you actually want. So, in order to do this idea of many different slope calculations, you need to know what the points are for 2 points. Well, we know the 1 point is 1, 1. That's the point that we're interested in. We will call it P. And then we got all these different values for Q. We're going to pick numbers that are closer and closer to 1 from either direction. So you start with 2, 1, 5, 1.1, 1.01, 1.001, and then 0, 0.5, 0.9, 0.99, 0.999. You can just keep adding 9s or adding 001s, and you get numbers that are infinitely close to 1 here, and you get these different y values with each one of these x values. Notice the function asks you to square your x coordinate to find the y coordinate. So you take each one of these guys and square it. And that's how I got the y coordinates here. So now what have I done down here? I've just done the slope formula with always using p and changing my q. So I used q1 with p. And so what do I get? I get 1 minus 4 over 1 minus 2. And it gives me an answer. And now I'm going to use P with this Q2. That's why I call it MP-Q2, slope of the line between P and Q2. So I'm saying 1 minus 2.25 over 1 minus 1.5. And then you do the same thing with Q3, Q4, Q5, and all the way down. And so what you see is as you get closer and closer to 1 here for your x value, you get closer and closer to 2 for your slope. And same thing over here, as you get closer and closer to 1 from below, you get closer and closer to 2 for your slope. So this definitely suggests that our slope is 2. But again, you have to do this. It's called a method of exhaustion. It was used by the ancient Greeks. So if you take your 2 points here, we know that P is 1, 1. And we know that if we plug in x into our function, we get x squared for the y coordinate. So here are your 2 different points. You can take x squared minus 1 over x minus 1. That's just the slope formula. And if you take this idea that we're going to be learning, which is called the limit, the way you read this is the limit as x approaches 1 of x squared minus 1 over x minus 1. equals this because you can factor the top, and now you can cancel those because they're the same value. And so now you're just taking the limit as x approaches 1 for x plus 1. Well, if this guy becomes closer and closer to 1, this guy becomes closer and closer to 2 because you're just adding 1 to it. So now we can pretty much say that our slope is 2, and we got the point 1, 1. So when you got a point 1, 1, you plug in your y1 and your x1 there. You plug in your slope that you say is 2, and when you simplify that down, you get the equation of the tangent line, which is what Newton wanted to figure out in the first place. Now this one tells you it uses a laser, and they give you a table already. These are the values that they give you in the table already, and they want to know what the charge is at 0.04 seconds after a laser is fired. And so the charge becomes smaller and smaller as time goes by. As the tenths of a second go by, you get less and less charge, which makes sense because the longer the laser fires, the more battery charge it's going to be using up. Now they want to know what's the rate of change of the charging of the laser at 0.04. Well, so then we're going to use all these other points with 0.04, 6.703. So that 0.04 is our point, P, and these other guys are our Q, or I called it R in this case. And it's just a matter of finding the slope with this guy in R1, this guy in R2, this guy in R3, this guy in R4, this guy in R5. And when you look at it, you see numbers that range from negative 82 to negative 50. They're all over the place. So what's the best way to calculate what's actually happening at 0.04? Well, to take the slope between R2 and P and R3 and P, the 2 points on either side of it. And those are these two guys here. And when you add them together and divide by 2 to get the average, you get this number. So that's a pretty good guess as to what your slope should be, the rate of change of your charge on your laser. Example 3 talks about the changing velocity of a ball as it drops through space, or drops from a height of 450 meters above the ground. And this is your formula that tells you the height of the ball after so many seconds. So after 0 seconds, 0 squared times 4.9 is 0. That means its velocity is 0 since it hasn't been dropped yet. And after 1 second, it's 4.9 meters per second. And then as you increase t, the velocity increases to a certain point. So now they want to know what's the velocity at 5 seconds. So what you need to do is find some points that are near 5. So you take 0.1, 5.01, 5.05, 5.01, 5.001, and you can keep going with this, getting closer and closer to 5. And you get these different y coordinates. And so now you've got 4 different q's here, and you get 1 p here. So you're going to use this p with each one of these points. And that's what you get here. And notice you're getting closer and closer to 49. And that's when we find out is that when the interval between 5 and another time interval close to 5, as that interval between 5 and that number get closer and closer together, we get a number that shows the rate of change is 49 meters per second. Now you can find it another way using what's called the difference quotient. Okay, the difference quotient is simply the plugging in x plus h into the function and plugging in x into the function and dividing it by some increment h. Now h is unknown, but it's a number that is infinitesimally small, and it just gets smaller and smaller and eventually allows you to figure out your answer when it approaches 0. So you take the original function with 5 seconds was our point of interest, and you plug 5 into the function and you get the y coordinate. And then you pick some increment that's slightly bigger than 5 with just some positive distance h or amount h. And then you plug that into the function itself and you get the y coordinate. So now you got the y and the x, you got the y and the x, you got 2 points, you can find the slope. So it's this guy minus that guy over this guy minus that guy, which gives you this. Notice your 5 and your minus 5 go away, and so you just get your h on the bottom. And on the top you get your function with 5 plus h and your function with 5. Now how does that simplify down? Well, this is how it simplifies down. You plug those numbers in, you multiply this guy out. Remember, 5 plus h is 5 squared, which is 25, and it's h squared, which is h times h, but you have a middle term of 10h in the middle there. So remember, when you square 5 plus h, you get a middle term that you need to remember. Gives you this guy here. You multiply each one by 4.9, this one by 4.9, negative 4.9. Your 1.122s go away. Your 5 and your minus 5 cancel, and you just get h on the bottom. And now if you've done this right, you should have only terms that have an h in them. Everything that does not have an h should go away. Alright? Now you divide h into here, and you get 49 plus 49h. Notice the h is divided into both of them, not just one. Okay, so now if you're looking at this and you let h be infinitesimally small, this part becomes meaningless, and this is your real answer. So if you let h be 1/1 billionth, 1/1 trillionth, 1 quadrillionth, whatever, just any number that's incredibly small, times 49 is going to be still incredibly small. And so you're looking at your slope approaching 49, which is what we thought it was. So all of these guys in this section are doing the same thing. They're just doing the slope formula over and over and over again. So here they give you the points, and they tell you to use 15,250 for your P. And all these other points, the first, second, fourth, fifth, and sixth, are your other 5 points, and you're going to have to do the slope 5 times with each one. P with this one, P with that one, P with that one, P with that one. And so you get numbers that are all over the place, but if you take the two numbers that are on either side of 10, 15, with 10 and 15 and 15 and 20, these are the two slopes you get. And if you average them, you get, add them together, divide by 2, you get this number here, which is a pretty good guess. Now if you draw the graph and you actually take a ruler and measure it out, you find that this distance of this triangle that's formed by the tangent line touching only in that one spot is roughly 300, and this one is roughly 9. And if you do the rise over run, you get negative 300 over positive 9, and that reduces to the same number that we found there. So that verifies that our answer was a good one. And this one does the same thing. They give you these guys here, and they ask you to figure out the slope between 0 and 40, 10 and 20, 20 and 30. Alright? And so eventually they want you to find out what's happening at the 20-minute mark. These are increments of 10 minutes each. These are the number of minutes after 3 p.m. So they want to know what's happening, how many steps you're taking on average at the 3 hour and 20 minute mark. And so you've got, this is your P, and these other 4 are your Q's. And it's just a matter of doing the slope formula with each one. Again, if you take the average of the numbers that are on either side, 10, 20 with 20, 30, you get 98.95, so the approximately 99 is a good guess for your slope. And that's the approximate walking pace at minute 20 minutes after 3.